Now it's better, right? Okay, so really sorry about that. So thanks very much, Matthias. And I'd like to thank the organizers for this invitation. It's a real honor to be here giving this talk. And also thank you to the local organizers for all their efforts in trying to make this in person, although at the end it couldn't be so. So I'm very much sorry I couldn't come to visit in Israel. So I want to tell you about a problem or a question we've been discussing in the last years, not continuously, but with my colleague from UPC, Jaume Martí Ferrer. Which is, so I want to tell you what's the question we looked at in about clutters and how our view of it has been changing and where we stand now. And well, you'll see a bit of a gap in the dates in the last 2 years. And Jaume and I were both vice deans at the math school. I actually still there. And sometimes it felt like I had like 200 children in addition to my 2 own. And things have been pretty busy at some point. But now things, well, as everywhere, things seem to be getting a bit better. So let's hope this is one of the last online conferences. So what's this about? So it's about clutter. So let's just to fix notation. Omega is just a finite set. And by a clutter, I just mean an antichain of subsets of omega. And I mean, some people call them simple hypergraphs or Sperner families, whichever name you like, we call them clutters. And so clut omega is just the set of all possible clutters on omega. So our motivation came from metroids initially. So to actually, there are clutters everywhere in combinatorics, in optimization, in cryptography. We were looking at clutters of metroids. So just you can look at, so we have a metroid on a finite set omega. There is a clutter associated to it, which is a clutter of circuits. So just I wrote down the definition just in case. It's a clutter that's not the clutter containing just the empty set, and the elements of the clutter satisfy this circuit elimination property. If you've got 2 circuits that have a common element, there is a third circuit that's included in the union of the first 2 and does not contain this common element. So once you've got the clutter, so the clutter of circuits, the clutter of circuits are the minimal sets that are dependent. So this the, let's say the upper set, the upset determined by the clutter of circuits. It's just called the set of dependent sets. Sorry. But well, to metric, you could say, okay, there's the clutter of circuits, but there's also the clutter of bases. So given a metroid, the clutter of bases is a clutter that's not the empty clutter, and then the elements of the clutter satisfy this basis exchange axiom. And I can read it down if you don't recall it at the moment. And then if you've got this clutter of bases, it happens that bases are just the maximal independent set. So given the clutter of bases, the down set it determines are independent sets. And actually, you could also associate other clutters to metroids, like clutters of hyperplanes or clutters of flats of a given rank. But that's just to stick to circuits and bases. So the general question is, if you give me an arbitrary clutter, lambda, which are the metroids that are closest to this clutter and closest? So this is a vague question. So which is could say, which are the metroids that resemble more lambda, or which are close to lambda in some sense? And just for a quick example, if you've got this clutter here, 1, 3, 1, 2, 1, 2, 3, 1, 2, 4, 3, 4, 5. Well, this is not a clutter of circuits because the first 2, they'll fail the circuit elimination property, but then you have at least two options to turn this into a clutter of circuits. You could say, okay, forget about the 5. The 5 is going to be in no circuit, and then we forced circuit elimination by adding 3, 4 to be a circuit. Or you could want to force 5 to stay in there, and then an option is to make a 1 to 1 5 parallel. So in all these drawings of metroids that I have, I always use the convention that a set of elements in the is independent if in the drawing they are affinely independent. So let's say in this first one, 1 and 2, they are 2 points on a line. So they are affinely independent, they are an independent set, but 1 to 3 are 3 points on a line. This is affinely dependent, so they are circuit, and this 3, 4, they are just sharing the same point in space. So it's 2 points, well, it's 2 elements lying in just 1 point, so they are dependent and they form a circuit. But as I said, you could also say, well, I don't want to look at clutters as circuits. I want to look at them as bases, and then you can just take this clutter and either remove one of the elements or add a bunch more to turn it into a clutter of bases of a metroid. And in this 5 in a box means that element 5 is a loop. And sorry about that, but the outside box doesn't mean anything. It just I just realized yesterday that was in the drawing, but it shouldn't. So it just to emphasize that these are on a plane. Okay, so this question is principle a bit vague for the moment. So there was some have been some efforts in linking clutters and metroids, and here are like the more relevant references we found. And most of these papers either take an approach of trying to make clutters look like circuits, or trying to make clutters look like bases. There's also the papers by Traldi. They use the analogy of clutters and metroid ports and try to see how clutters behave like metroid ports. So in several of these papers, what they try to do is to
just metroid what? I missed the word.
Metroid port. So a metroid port is just you take the circuits, you fix an element of a metroid, and you take all circuits that contain that element, and essentially that's a metroid port. It appears in cryptography in secret sharing schemes, for instance.
Okay.
So it's just another family of clutters that what would associate to a metroid. So in any of these papers, they try to either find an operation that takes a clutter and makes it somehow closer to a metroid, or either define deletion contraction operations in clutters, mimicking what happens with circuits or mimicking what happens with bases. And at the end, I reference Jaume's first paper on this topic. That is what make us started. And basically, he starting from a clutter, built a way to constructing a clutter of circuits. Okay, so let's see how do we approach the question. So given a clutter, as happens with bases and independent sets, so you can take your clutter and decide that this clutter is going to be like the minimal elements of an upset. So we denote by lambda plus all sets that contain an element of the clutter, so the upset determined by the clutter, and by lambda minus the downsets determined by the clutter, so all sets that are contained in at least one element of the clutter. So the clutter is either the minimal of the upset or the maximal of the downset. So circuits plus is dependent sets, bases minus is independent sets, just a reference. And then actually this this induces two partial orders on the set of clutters by inclusion of the upsets or by inclusion of the downset, and we'll call them the order plus and the order minus. So the order plus is just inclusion of the upsets, and you can write it down as just comparing the in terms of the elements of the clutter. So every element of the small clutter includes an element of the large one, and the same for the order minus. Okay, so we're working with these two orders, and then it's actually there's an easy way to move between these two orders and between one of the orders inside. So we call the complementary clutter is just you take your clutter and you take the complement of each of the sets of the clutter. And that's again another clutter. And then there is another operation on clutters that's called the blocker that takes your clutter lambda and just looks at all sets that intersects, all sets B that intersect all clutters, all sets of your clutter. And this is an upset, and you take the minimal of those. And it's known, this is well known that blocker is involutive. The blocker of the blocker is lambda. And what does the blocker, this blocker operation reverses the plus order. So it's easy to prove that. So by taking complements, you move from one order to the other. And then the blocker just reverses the order plus. So it's a sort of dual for the order plus. And if you want to reverse the order minus, you have to take complements and then blockers and then complements back if you want. So that's that would be a sort of blocker minus operation, just going to the usual blocker and back. Okay, and so just for some notation, there are these small clutters that sometimes are a bit annoying, or for the results that they are the ones that they lie at the extremes of the of the orders, and we'll call these trivial, and these two we'll call them co-trivial. So the empty clutter is both trivial and co-trivial. Okay, so just a quick summary. So for metroids, these two operations are essentially related to duality. So if you take the complementary of the clutter of bases, just by definition, you get the basis of the dual metroid. And you can check that if you take the blocker of the basis, that's the circuits of the dual, and so on. The complementary of the circuits are the hyperplanes of the dual metroids, and the blocker of the circuits are the basis of the dual metroid. And again, the complementary of the hyperplanes and the circuits of the duals, and the blockers of the hyperplanes. Well, they are just the blocker of the hyperplanes. I don't know of a way of expressing them better. And so this blocker essentially behaves, these two operations are duality-like, or are, at least for metroid clutters. And actually the orders are just, in many cases, are just the weak order. In metroids, you can just take it. It's actually the definition of the weak order agrees with the fact that this blocker of the clutter of circuits of M1 is below the clutter of circuits of M2. So just so these orders, they arise naturally in metroids, at least in some combinations. So we don't know how to express circuits with the order minus in terms of the weak order, for instance. Okay, so what we got? So the way we formalize the initial question about how close a clutter is to a metroid is we're going to fix a family of target clutters, or our favorite family of clutters, sigma, which could be clutters of circuits, clutters of bases, or it doesn't have to be clutters of metroids. It can be any family of, just for the same price, let's do it in general, can be any family of clutters that one likes. And there is this clutter lambda that we would like to see how far it's from our family. And so we defined four sets of clutters that they follow the same pattern. So if we take the order, we can take either the order plus or the order minus. Let's start with plus, and then I can look at all the clutters from my favorite family sigma that are either above my target, above my clutter lambda, or below my clutter lambda. So the U is for upper, because I want to look at the, we'll call this the upper completions. So the ones that are above lambda, and L is for lower. So we are looking at the ones that are just below lambda, and the same for the order minus. So for each fixed family sigma and for each clutter lambda, in theory, we have like 4 ways to approximate it. And so the first question is so you choose either upper or lower, and you choose one of the 2 orders. Is the set of approximations non-empty? And if it's non-empty, do the elements of these approximations determine my original clutter? So since when we are doing upper completions, we will be interested in the minimal elements, and when we are doing lower completions, we'll be interested in the maximal, which this minimal and maximal are the ones that in principle are closer to lambda. So this is just a quick example. So you take the non-Fano metroid. So this is Fano, the Fano plane. This is non-Fano, which misses this 3-point line. And then, so non-Fano is a non-binary metroid, but I would like to know which are the binary metroids that are closer to non-Fano. So I would take sigma as, for instance, the set of circuits of binary metroids, and then I want to know which are the metroids that are closer to non-Fano, let's say above, which for circuits makes slightly more sense. So I would take, okay, let's take the order plus, which is the weak order, and let's try to find which are the metroids above non-Fano, and then, okay, at the end, it's an exercise in weak orders, and you end up finding that you've got the Fano metroid, which not surprisingly, and then 8 other metroids, which they, in terms of isomorphism, they fall into these 3 families. And here you can play, and this can be any of the odd numbers. And this one, just you've got this one, and then this one also, you can play a bit, switching making some permutations of the numbers, but essentially they look like that. So in this case, there would be like 9 minimal metroids closer to non-Fano, 9 minimal binary metroids closest to non-Fano above. But actually, if one wishes to recover the non-Fano metroid from this 9, it's enough just to take 2. So you take well, not any 2, but in this case, if we take the Fano metroid and then any of these 8, we can recover the circuits of non-Fano by just taking the minimal elements that look like that. You take a circuit of one and circuit of the other, And then you make the union, and then you take the minimal elements of all that, and that's class of circuit of non-Fano. Okay, so this is for example of what we aim at. So informally, the result we had looked like that. So it said, okay, you choose any of the two sides and you choose any of the two operations. And then there is a special, well, we call it somehow a special family of clutters. It's called F, that depends on these two parameters, plus or minus or upper or lower, such that if the favorite family sigma contains this special family, then for sure there will be some approximation of the clutter by members of sigma. And moreover, if we call lambda 1, lambda r the elements of sigma that are closest to our clutter with respect to the operation and the side that we choose, which we call the optimal completions. This just means that if we chose upper, this will be the minimal elements of this sigma square S lambda. And if we choose lower, there will be the maximal. And then there is an operation that allows us to recover the original clutter in terms of these optimal completions that somehow called the decomposition. And that's the general framework. And that's what, and this sigma can be just any family of clutters you like. So at the end, we realized that these operations that we had there, they are actually just turning the set of clutters into a lattice, and that allows to rephrase the previous result in a much easier and clearer way. So for let's say the plus order, we got these two operations that just takes so we take the two clutters, the upsets they determined, we intersect them, and they take the minimal elements, and that's the meet in clutters plus. And the join is you take the up families, you take the union, and then you take the minimal of those. And the same for clutters minors, just analogously with respect to the downset. And the operations transformations we had before, like complementary and blockers, they behave perfectly well with respect to this operation. So the complementary just moves from one lattice to the other, respecting joins and meets, and the blocker, it interchanges join and meet in the plus lattice. So this is the free distributive lattice labeled by clutters, and they are like, depending on which order, when the order plus or the order minus, well, the clutters are put in different places, but actually the structure is the same. So we'll speak of a sigma meet decomposition of lambda is just writing lambda as a meet of elements of sigma in either lattice, and we'll speak of a sigma join decomposition of lambda as if we can write lambda as a join of elements in either lattice. And then what lattice theory tells us is that there will be a decomposition in the order plus for all, let me get rid of trivial clutters, if and only if your favorite family contains the meet irreducible elements of the lattice. And in this case, the meet irreducible elements of this lattice are just these ones. They are formed by, they are the clutters that are formed by any number of singletons. So for short, if you've got sigma and you want to know if for any clutter that's there is the composition of your clutter lambda in terms of the elements of sigma, just have to check if the family sigma contains all these clutters. And if yes, there is this decomposition for any clutter lambda. And if not, well, there is no decomposition in general. There might be in some cases, but not in general. So, and analogously for all the other, orders and the other sides. So you got the join. Well, once we have the meet irreducible, we can just take complements and blockers and find the others. So I put them here, but I think picture is maybe easier. So the orange guys are the meet irreducible in either lattice, that they are at the same places, but they are labeled by different clutters, and just easy to check that one is complement of each one is a complement of the others, and the join irreducible on and actually the join irreducible are exactly they are the same in the sense that they are the join irreducible are the clutters that just have one element. So the one set clutters, let's say. So the complements will be also one set clutters. Okay, so this is just a summary of what I was saying before. You've got the meet and the join irreducible for each of the combinations. And then the decomposition and the optimal completions exist for all, let's say, non-trivial, non-co-trivial clutters to avoid the extremes of the lattice, if and only if your favorite family contains the meet irreducibles or the join irreducible, depending on if we're going above or below. Okay, so if we go back to the metroid case, which was our initial motivation. So now it's just a matter of checking if those join irreducibles, meet irreducibles are clutters of circuits or clutters of bases, and actually it turns out quite easy to check. So now, if you've got a bunch of singletons, these are clutters of circuits, because you can have just impose that all those elements are loops and the others are co-loops. And they are also bases, because you could have this bunch of elements in parallel, and individually each one would be a basis and all the others are loops. So they bother. And the one element clutters, they are clutters of circuits. And they are also clutters of bases. And here are the description of the metroids if you're interested. But actually they are very simple metroids. They are just uniform metroids. And when we take the complement of the first one, so they are also clutters of bases. So these are clutters of bases, but they are not clutters of circuits in general. So this says that if all these in all these combinations we had, that's going up or lower and in order plus, in order minus, the only in which there is no sure decomposition is when we would try to approximate by circuit clutters in the order minus above, which that doesn't imply that in some particular cases. So in some cases there will be decomposition or there will be completions. In some others there won't. But in general, things we cannot ensure that they always work fine. Okay, so once so for all other combinations, we know that these exist. But the question is, okay, they exist, and now how we find them? Is it possible to find them, to see which, just to construct them somewhere, somehow? So if by combining blockers and complements, so it's easy to see that the first three cases, so the first three are equivalent somehow, that you can go from one to the other, provided you take complements, which, okay, it's easy, or you take blockers, which is not easy. So in terms of computationally, taking blockers is not easy at all, but in theory, these three cases, they amount to the same, and the next three, they also amount to the same, and then this one goes on its own. And so the first case, the one of trying, which somehow for circuits is, I think it's the most natural one, which is trying to find metroids above your clutter in an order that it's akin to the weak order. So this is what Jaume did in his paper. And so given our initial clutter, there is an algorithm that produces the minimal clutters that are just that are clutters of circuits. So that are matroidal clutters of circuits, and they are just above lambda and minimal with that condition. And this is related to a result of Dres and Wenzel, that what they did is given a clutter lambda to construct a clutter of bases that lies just below lambda in the order plus, which is by taking blockers, one thing is equivalent to the other. What happened with so this construction of Dres and Wenzel was by applying some closure operators and seeing when the application stabilizes, and somehow so this construction, they noticed that sometimes it just goes down further down to the bottom of the lattice. So it just starts from lambda and goes just to the bottom and doesn't stop, even if there were some basis clutters just before. Okay, so the other two, so basically we prefer to, or find it easier to work with circuits. So all these, how to find this completion for the three kinds of circuits. So the first case is by Jaume, and the other, we completed the other two. And they all, let me tell you a bit quickly how this goes. They all use this idea, given two elements of a clutter, we do this intersection. You take all the elements of the clutter that are contained in this union, and then we intersect them all. And just by using circuit elimination, it's easy to see that a clutter will be a clutter of circuits if and only if this intersection is empty for any pair of elements of your clutter. And this, somehow it's more usable as circuit elimination. So we find this more usable than just the direct circuit elimination. So for instance, let's look at this case. We are in the order plus, and we want to find clutters that are circuit clutters below our target clutter lambda. And basically what we do is one takes lambda and takes a set of that clutter, and then one looks if there is some other set in the clutter for which this intersection I lambda is non-empty, which means that this wasn't a clutter of circuits. And then we define this transformation beta that says, okay, you take your clutter lambda, you remove that set that was giving problems to circuit elimination, and then you add back that set with every element that wasn't in that set. So we remove one and we add back a bunch of sets, and then we take the minimal of this in case that wasn't a clutter. And so I'm using all the time the convention that when I'm just adding one element or removing one, I'm not writing the brackets. Okay, so basically we do that. We just transform the clutter. If we notice that circuit elimination fails, and otherwise clutter stays the same. And then well, it's most immediate to show that this beta lambda is the clutter that's below lambda. So we are going down in the lattice, which is what we want. And if beta lambda A is lambda for all A, then it means that lambda is a clutter of circuits. So what it happens is that if if we have an optimal completion lambda prime of our set lambda, which means that lambda prime is a clutter of circuits below lambda, and there is no other clutter of circuits in the middle, then we can prove that we can go from lambda to lambda prime by successively applying this operation beta. So this beta goes down the lattice, but goes little by little, and it doesn't miss any completion. So basically, if we want to obtain, so this is more on the theoretical side, I'm afraid. So if I want to obtain all optimal completion, I would apply this beta transformation in all possible ways and orders. And when no more application, when it's not possible to apply it more, just take the maximal clutters that I've generated, and those would be the optimal completion. And I had an example here, but maybe I'll put it a bit quickly. So one starts with this 2-element clutter, which is not a circuit clutter because well, clearly circuit elimination fails, and this I lambda is 1. And then what beta does is just to remove sets and add them back. So here we removed 1, 3, but then we add, sorry, 1, 2, 3, and then we added 1, 2, 3, 1, 2, 3, 1, 2, 3, 5, but 1, 2, 3, 4 was already somehow there because we had 1, 2, 4, so we got this one. And we keep going, and then at some point we reach this 1-element clutters, and which these are circuit clutters, that's fine. So, but we still, so no one has to do this for all the lambdas that we keep producing, and for all the sets there that fail circuit elimination. So it easily explodes. And then essentially one sees that there will be nothing else. That at some point we will reach to this clutter, but then all sets, they contain 1, and this will not be a circuit clutter. So what this beta transformation will do is eventually get rid of all of them until 1 is left. So basically, I mean, this is just a toy example, and that I agree it's quicker to do it by hand than just to apply the transformation, but just wanted to give you a flavor of what's about. And then, for instance, we can do the same for the other types of circuit completions we have. The algorithms look similar, maybe slightly more. Well, there are a couple of cases instead of just one transformation, but they look more or less the same. So here I've got another case that if we were doing in the order minus that same clutter, then instead of 2, we'd find 4 completions. But actually, of these 4, there are 2 that suffice to recover the clutter with as a join. So I mean, it's natural that things happen because if these are not join irreducible, so there is the decomposition is not irredundant, but somehow these clutters for which only 2 matroidal clutters are needed to decompose them, to me, they look like the more like targets to be metroid-like clutters. So they are the ones that they are almost there, but not metroid clutters. Okay, so let me now tell you about the last thing I wanted to tell you about. So until now, there were clutters in general. So a clutter could be just anything. And we were looking at the family of all clutters on a set omega. But maybe we're interested in clutters. So we don't want to look just at any clutter, but we want that the sets of our clutters, they cover the ground set. So it could be that if we are looking at, let's say, clusters of bases, if our metroid has loops, well, there will be elements that are in no bases, and then the cluster of bases. So there will be an element that appears in no set of the cluster of bases. So we would like to avoid that. So we want to restrict to this, well, we call them clusters with ground set. So it's just the clusters that cover the ground set. And this, in terms of metroids, would be looking at metroids that are, well, if we are looking for bases at loop free, or if we are looking at circuits, metroids that are co-loop free. But it becomes more natural also if your clusters are suited to graphs, like they are like minimal, for instance, minimal dominating sets that have been looking by Jaume and his co-authors. They naturally belong to this class. And for instance, if we were looking at the cluster of maximal independent sets of a graph, that would also be a cluster that covers the ground set, since every vertex is in some independent set. So want to restrict to this family. So and the idea would be the same. Give me a cluster in that family, and now the favorite clusters are also belong to this family. Can we approximate lambda by clusters of the family sigma? Can we decompose lambda by clusters of the family sigma? And well, now we know the trick somehow. So let's look at the lattices. And so this in red, they are in either lattice the clusters that cover the ground set, so those that contain all elements. And clearly on the right-hand side, on the minus part, this red part looks quite, well, it looks clearly like a sublattice of the big one. And here in the cluster plus, the elements are a bit more scattered. They still, in this case, they are still nicely ordered and lattice-like. So let's see what happens. So for the order minus, so comparing down sets, if you wish, it's indeed, so the ones that cover the ground set are just as sublattice, and they are just the ones, well, here you'll see these are, the red ones are the ones that are above the cluster that has all singletons, and that happens in general. And then it is to find the meet irreducible elements and the join irreducible elements that I wrote down them here. And so it would just work just as before. If you are interested in this decomposing, just look if the meet and the join irreducible are there, and if there are, fine, and if there aren't, you don't have the guarantee that it will always work. But for the order plus in general, there is no lattice structure, and you can find elements that have two maximal upper bounds. So, for instance, so the framework before doesn't apply in this case, and but still, what we have is that we have one of these clusters that covers the ground set. Then the blocker operation also covers the ground set. So at least this this sort of we do have an involution on the set of clutters fixing the ground set. And so for the case minus, there's nothing to do because it follows the same framework as before. And for the case plus, so we found what were the elements that would play the role of the Mier-irreducible elements. So we say, okay, let's look at these clutters, which this is all singletons, which in the order plus is just at the very top. And then you take all clutters that are formed by pairs that contain one. So it's pairs that one element with all the others, and for all possible permutations. And then we also have these clutters that are, a few of them are singletons, and then the others are all pairs of one of them with all the others. So it's a mix of the two. And these clutters, what happens is that they play the role of the Mier-irreducibles. So if we want to, if we have, like as always, a favorite family of clutters covering the ground set, and we want to decompose a clutter lambda in terms of those with in the plus lattice, which now restricted to covering the ground set is no longer a lattice, then there will be a decomposition if and only if your favorite family includes all of these. Which sure, you can see quickly that for metroids it won't be the case. And the same if we were interested in sigma joint decompositions, we'll just take blockers of this, and it's to compute those blockers, and that would have the same structure. So how much time do we have, Matthias?
Well, we started a few minutes late, so you have a couple of minutes.
Okay, so I had included the proof of this just to give you a flavor, but let me maybe just go quickly over it. So what? Well, the first one has to do is to check that this M0 plus family, which were like all singletons and then pairs of one with everyone and a mix, they are irreducible in this lattice, and one checks that. And then one does is, okay, I take my clutter, I look at all the ones that are above lambda in sigma and take the minimal ones. And there's always some because I made sure that the top element is always there in sigma. So this exists, and then you take the mid of all these elements, and then you go on checking that this is exactly you. So the mid of all these, let's call it lambda naught, and you want to check that this is exactly lambda. So it's easy to see that lambda naught it's above lambda, and let's assume it's not below. And then just by the definition of the order, it says there must be some element here in lambda naught that such that no subset of A is in lambda, and then one uses that lambda covers the ground set. So since lambda covers the ground set, this A1 should be covered in lambda, but cannot be, this A1 should be with someone outside of A, because no subset of A was in lambda. So this A1 is with someone else, let's say with a R plus 1. And then one takes this clutter, which is one of the ones in M plus naught, which by assumption is in sigma. And we skip the details. One eventually shows that this lambda head is above lambda, so it's above lambda and it's in sigma. it should be above this lambda i's, and then it should be above lambda naught, but in the way it's constructed, it cannot be above lambda naught, which is a contradiction. So in conclusion, it has to, so conclusion lambda naught has to be below lambda, and so it's above and below, and it has to be exactly lambda. So if one forces this m naught plus to be in sigma, then the elements of sigma that are above lambda, they decompose the clutter. Even if now we don't have a lattice structure, these behave like if they were Mier-reducible elements. So let me finish by just a few questions that somehow still intrigue me. Well, one is that, so the finding matroidal completions, the proceedings that we have in practice, they are, well, they work, so theoretically they are simple, but when you try to apply them, there's just too many clutters that arise, and it grows too fast to be able to control them. So one thing to think about is that if one can do better finding these matroidal completions. And another thing is what I mentioned before, that so if one aims at trying to find clutters that are Metroid-like or the most Metroid-like, so my candidate would be the ones that have exactly 2 optimal completions. So the one, or the ones that can be written in terms of just 2 of the clutters they have above or below. But, so I think it's a class of clutters worth giving them a good look, but we haven't had the chance to do it yet. And finally, for this last situation, when we want to restrict to clutters that cover the ground set, so I would like to have a, well, we don't know if there is a lattice analog of that, especially for the plus order. So we trying, especially Jaume was trying quite a lot to find a way of defining what it means to cover the ground set for an arbitrary distributive lattice. And we have some ideas, but they are, at the end, they're a bit involved, and it seems that let's say they don't apply to much beyond the, or we don't have a good example beyond the lattice of clutters. So if now if you have a feeling of what covering the ground set could be for an arbitrary distributive lattice, I would be happy to hear. So thanks a lot for your attention. Also, if someone had woke up earlier than usual to attend this talk, so thank you.
Thank you, Anna. Thank you for this very nice talk. We have time for, well, a question or two.
So I have a question and also a remark. So there is a generalization of matroids. There are 2 classes. One is called supermatroids, and another, which is made by me, Fujishiki, and Sana, it is matroids on convex geometries. And so therefore, if we just look on such clutters which correspond to this, then I think there is a strange question just to try to find matroid, which is correspond to generalization. So therefore, I will propose you, so maybe just to look on your problem from the viewpoint of that these generalized structures.
Mm-hmm.
Thank you.
Okay, yeah, so you said supermatroids and matroids?
And matroids on convex geometries. And also then you consider distributive lattices. This is a particular case of convex geometry. So you can look on convex geometries, not on the on distributive lattices. So these more nice structures.
Okay, good, thanks.
Any other questions?
So I'm not in the field, but it really reminds me some concept, the concept of blockers and in convex geometry that I heard in Hebrew University when I was young. But I don't know, so geometry in this could be interesting.
Mm-hmm. Yeah.
Continuing Gleb's question, you can think of other variants of matroids like gridoids, which are larger family, or matroids which are representable over a specific field or not specific field. So did you consider such variants?
Yes, so at some point we were looking at the case of a representable matroid. So taking like your target or your favorite family would be like in that case of non-Fano, for instance, that you want binary matroids and you take your clutter, which could be of a matroid that's not binary, and then look at it and see which are the matroids closest to it in the weak order or in whichever setting it. But so this theoretically sort of exists, but I don't know of any way to produce them nicely, or at least theoretically.
Thank you. Maybe I just have one very quick question. What is so special about one of those families, about the CU minus? Why is it different?
So what happens is that the Mier reducibles in the minus lattice, they are not clutters of circuits. Mm-hmm. So really the general framework doesn't apply to that. But you could, so in some cases then strange things happen when you take a clutter and there are some clutters of circuits above it, but they don't decompose the clutter, or so it's just a case where you cannot say that things will work nicely always, so to speak.
Okay.
But,
okay, so thank you.
Yeah, no, I have more intuition on that. Sorry.
Thanks.
Thanks.
So if you could please stop
sure.
your slides. Thank you very much. And Nick, you can start sharing yours.